Hello everybody, my name is Tomi Nihtilä. I come from Tampere, Finland, and I'm going to present the acoustic imaging experiment we did just using off-the-shelf audio hardware in a just normal office room. This is quite like a practical approach. I am not going to present any mathematical formulas. So, outline of the presentation, why I did this, and then I'm going to open a little bit of that long title with plenty of keywords. What do they mean? And present the measurement system I used and some results and conclusions. So our group, research group, we have a background in radar signal processing. We have been doing radar things in cooperation with the Finnish military. And one hot topic in radar signal processing is synthetic aperture radar, which means that you can form an image using radar, like a map of the surroundings from a plane flying high altitude. So there was just an idea that can we actually do the same with sound? So we could maybe try a little bit with the real data instead of always simulations, although sometimes we also get real radar data. And the image reconstruction method we are using, it's also a little bit different from what is usually used, at least as far as we know. So this is the really professional equipment, a lot of duct tape and foam. So we're just using some device we could find at the department. So just a normal audio speaker, active speaker, cheap Behringer microphones. There are 8 microphones, but actually in this example I'm presenting we are only using one. And then we have a 8-channel USB audio interface for recording the microphone signals. And everything is controlled by MATLAB and Simulink. So when we're doing image with radar or sonar, we want to have a big aperture to have a narrow beam, and with narrow beam we can have a high resolution typically. But there are usually practical constraints. We cannot have too big aperture. So one way of enlarging is to use synthetic aperture. It means that you're moving either the radar or the transducer or the object. So basically, for example, a plane flying with aperture of this size, looking side, sending pulses, and processing this time, you have aperture of this size. So what we want to have in that is the change of aspect angle. We can see the object from a little bit different angles to have a resolution in that cross-range domain. And then with high bandwidth, we can have a higher resolution in downrange. There is just an illustrated picture of inverse SAR where you actually have the radar is stationary and the object is moving or turning around. So usually you have one of these, but in this controlled experiment we can have both large angle and high bandwidth. And when we have made the measurement, we have a matrix of data with 2 dimensions. One is the downrange, one is the cross range. Like fast time and slow time usually we call them. One is the angle and one is the downrange. And while image reconstruction methods usually they change the data so that you can use Fourier transform or FFT, which is of course good for fast computation. But we wanted to keep the data unaltered and actually find the kernel functions for the transform based on how the object is moving. So just a little bit different approach. So what we kind of imagine if there is a turning object, you have an empty image grid, and you start turning it, and you are kind of simulating data. What happens if there is a point scatterer in each pixel? You create that for each pixel, and then you have a kind of matched filter for the data to compute correlation with the data you have measured. And while you do this for every pixel, it takes a lot of computation time compared to other methods. But you can also just compute individual pixels or parts of the image. If you don't need the whole image to be computed. And this similar method was presented by my colleague 2 weeks ago in European radar conference for radar applications. So this is how it was, the measurement. This is our test object, which was just used for the first experiments, and it ended up being the last one also we used. So just a piece of wood, 2 bolts, cardboard, plastic bottle, just to have different materials from different distance from the center of rotation. So inside this thing, we have a stepper motor controlled by Arduino. So we are turning this thing around as 400 steps per revolution, so 0.9 degrees per step. And the environment is like this is a normal small office room. We have 2-meter distance and walls and ceiling and everything at close proximity, having strong static echoes. And this method and what we are using, it may sound a bit stupid. Why would you just use some efficient tomographic algorithm? Yeah, it's true, but this was just to test the method with some way, and it's easy to just rotate an object, especially when you have to do it just in an office room. So the measurement itself, this is the online part. We are doing the processing offline. We are using quite short pulse. Actually, the pulse length is like these 2 meters, so that we don't have the direct response from the speaker at the same time when we are listening to the echoes. So we send a pulse, record the echoes, rotate the object 1 step, and then we need to wait a little bit because this thing is not very stable, so it's resonating for a while after the step. Then we store the data. And yeah, the pulse is frequency modulated, using almost the whole bandwidth of the speaker and microphones. Then we have the data, and then we organize the data to have this measured matrix. It's kind of synchronizing in a way that the data needs to be coherent. That if we have a reflection from certain distance, it always produces the same phase. So it's just reorganizing the data. Then we have pulse compression, meaning we are using the send pulses matched filter to have the range profiles, like one-dimensional projection of the acoustic reflectivity. So here you, for example, see that this is the direct response coming just from the speaker to the microphones. And then it's nothing, and then we have here the object, and then this is the wall at the background. Then we use range gating and high-pass filtering to get rid of these, the direct response and the walls and ceilings and everything. It's just basically subtracting the average from the whole data. It just works. And after that, when we organize all the data together, we have like a scenogram. Use the name, I think, in tomography, in CT. So here, we have like 4 dominant scatterers in this object. They all, because it's rotating, they all throw a sine wave then here in the sinogram. And then we start correlating this data with the kernels we created before. And do windowing. We're not doing for the whole revolution at once. Just a different visual evaluation for that. So the integral transform is that we use those kernels as a matched filter. So what we do in that, creating the kernel in this case when we have rotating object, we have like all the possibilities of these sine waves here. So what we get, we're first also simulating this to just see that the method works, that there's nothing wrong in our measurement. So this is the simulated one. We didn't simulate the wooden part, so that's why it's only those 4 scatterers. And this is the computed from the measured data. So this is the plastic bottle, these 2 are the balls, and here's the piece of cardboard, and then the wooden stick. And also something a little bit from the center, although it's tried to be covered with foam. And the data here is constructed from 4 90-degree segments. They're just incoherent, just summed together. And here is some experiments with different segment sizes, like how long we integrate. We can also integrate the whole revolution. But especially when you look at it close, you see that it's not the best to do like theoretical the maximum resolution. So there is a concept of acoustic imaging using possibly cheap components. Although here the speaker was not cheap, but you could use just some cheap speakers and maybe just some calibration for the frequency response. And the reconstruction method, it works equally for different kind of geometries because you just need to know the geometry. Also in this case, it's actually computed as bi-static, meaning that the transmitter and receiver are not at the same point. And it works for something else. This is with radar. That's from the paper from my colleague. So this turntable, big turntable, and they're using this experimental radar with really high bandwidth, 1 gigahertz or something like that. And this is the image of the car, the same method. And some ideas. I would like to try this 2-dimensional ultrasound MEMS microphone array. And actually, I saw something like this here in this conference, so maybe we will try the image reconstruction for those signals. So, thank you.